Hello. So I just wanted to record this video real quick to go over the first half of Unit 3. So hopefully you guys had time this break or this past week to do those practice questions. So you should have done half of the Unit 3 progress check. So the multiple choice questions and the FRQs. So I'll go over that today. All right. Okay, so these are the 5 concepts. So I split this unit 3 up into 2 categories because this first half is more based in ecology. So it's about our natural world, while the second half of unit 3 is more about the population of people and what influences that. All right, so some of this, if for AP Bio, it should be review, but I will start with 3.1 and just go down the line. So we'll talk about generalist and specialist species first. Okay, so just a reminder for that vocab word of niche. So niche is like a role or a position of an organism in an ecosystem. So like for me, I am a teacher. I am also like a daughter. I have a lot of roles and positions in Oakland. Okay, so like most species, not most, a lot of species can be broken up into generalists and specialists. And what you need to know for the AP test are like specialists have a very narrow niche. And what that means is that like, I think I covered this in the last section, but a specialist is like a koala bear where they can only really eat like, I think it's like bamboo leaves or something. They can only like sleep in certain trees, and same with pandas, right? They're not very adaptable. So like if all of a sudden those trees went extinct, the koala would be like shit out of luck or something. They're more likely to become extinct because they're a little bit more fragile in the resources they need. And they're easily affected by like climate change or like if their habitat is altered. So they thrive when like conditions are more constant. So that's specialists. So like they specialize in a particular niche, while you have on the other side of the spectrum, they have generalists. So generalists are things that are a little bit more common, like squirrels, wolves, coyotes, like they fit in a lot of different places. So they have a broad niche. They can adapt to a lot of different climates and a lot of different available resources. They can kind of make do, like mice and raccoon, like you find raccoons literally everywhere. They're less likely to become extinct. The idea of a squirrel becoming extinct is very laughable to me, and that's because they're generalists. They can use a variety of resources. They have a high tolerance of different environments, and so they're the most adaptable. Is like during climate change. Like climate change, they say, is like not going to really affect like rats and mice and like cockroaches and ants and stuff because they're the generalists and they can adapt in a lot of different environments. So that one's a pretty simple concept to grasp. Okay. So this one, so the K selected and R selected species. So these two concepts, this concept is going to continue to build with the rest of the concepts that are covered in this part of the unit. But so R selected species are, so there's a characteristics for R and K selected species. So for R selected species, there are things like species that have a lot of offspring. And so like, as you can see in this dandelion, each of these seeds is an offspring. Or like mice, for example, will have like a bunch of baby mice in each litter. Low investment, what low investment means is that like oftentimes the parent of whatever species it is will abandon their young or only take care of their young for a short amount of time. So that's what they mean by investment. So, and usually the R selected, there are selected species, most of the offspring will die before they mature. And so if you think about things like turtle eggs, like baby turtles don't usually survive to adulthood. And so there are a few that do. Most of them have shorter lives as well for our selected species. Superficial relationships, meaning that's a funny way to put it. Just meaning that like they maybe like will mate with several of their other species, and they're usually not high investment in with whoever their mate is. So okay, so those are things like ants are selected. There are mice are selected because they have a lot of offspring, like I said before, have a shorter lifespan. Or like, for example, grass. Grass don't live very long. There's grass produce a bunch of seeds. They don't take care of their offspring, right? So that's R selected, while when we move over to the other side of the category is K selected. So K selected are usually like bigger creatures, larger, and so they have fewer offspring. So for example, what this picture shows is that like the humans are considered K selected species. So we can only have really like most families will have like 1 to 3 children, right? And high investment meaning like K-selected species invest a lot in their offspring. You know, like for humans, we take care of our offspring until they're 18 years old or older, right? You would never see a mouse do that, right? Or an ant. So with another thing aspect of K-selected species that you should know is that most K-selected species that are born have a really high chance of reaching maturity, which is reaching like adulthood, right? And so that's how humans are. And then also they have a long life. And so rich relationships, I think rich is a funny word to do it. Rich relationship meaning they like mate with like only a couple of different organisms in their lifetime. So their investment in like their mates are a little bit higher. All right. Okay. So like elephants are K-selected creatures. They live for a long time. Their young usually sticks around for quite a number of years. Their offspring or their young. They only have like a few baby elephants a year. And so the same with like, see how these are like larger species. So like the jaguar is also one of those. Most wild cats are K-selected creatures, sharks as well. It's a large creature. And so it has fewer offspring. All right. So those are K and R selected species, and we'll revisit that in the next concept. Okay. So this is where, so I'll talk about the K and R selected species in a second, but remember in those species, we talked about like the number of offspring that will survive into adulthood. So ecologists have found a way to categorize species by how they their likelihood to survive. So they have categorized it as type 1, type 2, and type 3. So in this graph here, you can see that you can see that the x-axis is like their age. And so their age by like approximately years. It says age in relative units. So like, you know, it's an approximation. And then the y-axis is the number of survivors. Okay, so what this graph is saying that is this red line, which is type 1. Type 1 say that there are 1,000, let's say like of a species, which say humans. If there are 1,000 species born, the likelihood of all of those species surviving stays pretty constant, right? And so what that's saying is that the type 1 species, when they're born, they'll usually survive into adulthood. So it's like they survive into adulthood and then they start dying of old age. So that's why the curve stays pretty constant up here and then drops drastically when they're older. All right. So let's look at the opposite, which is type 3. So down here in the green is the type 3 curve. Now, the type 3 curve is the opposite, which are species whose offspring don't, only a small percentage of the offspring survive to adulthood. So you can see like if 1,000 of some organism, let's say it's like the acorn of the tree. So if 1,000 acorns drop into the ground, only a few of them will grow like shoots, will grow like little, grow a little bit out of the ground. And then the likelihood of them becoming trees is very low. So you can see like how many survivors there really are. But then if they survive into adulthood, they will continue, they will live. See how it levels off right here, which means that the survivors are staying alive until they reach a certain age, whatever the end of their lifetime is. All right. So, and then type 2 are kind of like the intermediate species where there's like a 50-50 chance that the offspring will survive into adulthood. So those include like birds are oftentimes categorized in type 2. And so just like what we talked about with K-selected species, oftentimes the K-selected species fall into the type 1 survivorship curve. All right, because they're bigger. Usually if they're born, they will survive into adulthood. While on the other hand, as you can probably guess, the R-selected species usually fall into the type 3 survivorship curve, where a bunch of them are born at once, and then only a small fraction of them survive. All right. Okay. So now I want to now I want to like kind of broaden the scope a little bit and talk about populations of species. So we kind of talked about how ecologists categorize species based on how they like occupy an ecosystem. So now I want to talk about how a population grows based on the ecosystem that it exists in. So carrying capacity is talking about when a population reaches its limit. All right. So, okay, so let's look at this graph here. The x-axis is over time, right? And then the y-axis is the population size. So what this is saying here is that with unlimited resources, so if there's unlimited food and shelter and whatever other resources that species needs, there will be exponential growth. So this growth will just keep growing up and up and up and up if there's an abundance and an unlimited amount of resources. Now, we know that on Earth, that doesn't exist, right? You cannot just find an ecosystem that has unlimited resources. So what realistically what happens in most ecosystems is that there's logistic growth. So remember logarithm? So same graph, but instead of just continuing to grow exponentially, at some point it gets capped. And so where this graph becomes logarithmic is right here, and it's because of this line here. So maybe this line is like, okay, this like grassy field can only support like this many deer, right? And so then the deer population there will get capped here. And this line is what you call the carrying capacity. All right. So maybe that population size is like 200. So this grassy field can only support 200 deer. All right. And that's the carrying capacity of that field for deer. All right. So to think about carrying capacity in a little bit more depth, I want to show you this graph. So here you can see this is a more realistic depiction of what would happen if like a species were to be introduced into the ecosystem and its growth pattern over time as an entire population in an ecosystem. So again, you have time and you have population again here on this graph. So, okay, so say like, for example, a bunch of ducks were introduced into this pond. And so there is a whole bunch of resources for this ducks. There's food, there's available water, there's available shelter. And so the population grows exponentially. Now, all of a sudden it hits the carrying capacity. Maybe like the amount of habitat starts running out. There's too many ducks and they're populating too quickly, or there's not enough plants for the duck to eat, right? so then what happens is that carrying capacity hits. So of course, carrying capacity is the amount of organisms within a region that the environment can support sustainably. Okay, so it's reached the carrying capacity, but of course it's going to overshoot it a little bit. So what's going to happen that the overshoot occurs when the population growth exceeds the carrying capacity. And what's going to happen is you're going to see this crash, or as ecologists call a die-off for individuals in the population. So all of a sudden you see this die-off that happens here. And of course it rebounds past the carrying capacity. And so what they're saying is that it starts then just kind of like going back and forth. So it'll die off, it'll go below the carrying capacity. So then they're like, oh, okay, we have some more resources that we can support an even bigger population. So then it'll start growing exponentially again, just like it did here. And then it'll crash again once it realizes it's out of its carrying capacity. So of course, this kind of like undulating that it does in the environment is also damaging to the resources, right? So what happened, why like all of a sudden this carrying capacity starts decreasing is because the degraded carrying capacity may be due to resource destruction during an overshoot. And carrying capacity is not static, meaning carrying capacity doesn't just stay where it is at all times. So like maybe the duck like had eaten so many plants to survive during the die-off, going back and forth, that the plants are having a hard time coming back. And so since there are less plants, the carrying capacity of the ducks goes even lower, right? So know that carrying capacity is not stagnant and is not to stay the same. It changes with the ecosystem and with what's going on in it. All right, so that's carrying capacity. Now, I want to, so the last concept kind of like ties everything that we talked about in this unit together. So what happens with, so, oops, I did not, that's okay. So with 3.5 talks about population growth and resource availability. So we're kind of just going to stitch together like the other concepts that we just learned in unit 3. So I think that in one of the videos, I took a screenshot because I thought this was a really good way to depict it. So there are 2 different ways that an ecosystem is influenced. An ecosystem's population is influenced. There are density dependent factors, and then there's density independent factors. So, okay, so density independent factors are things that happen to an ecosystem that affect the populations that live there, but are not dependent on those populations. So for example, like if a hurricane just comes in and destroys a wetland, that hurricane didn't really care how many ducks were in that wetland, right? And so that would be a density independent factor. Okay. Now, or like, so those are density independent. Now, density dependent usually have to do with what's happening within the population. So density dependent would be like, oh, those plants have been eaten too much, and now there's a lot of competition between the ducks to find plants to eat, right? Or maybe coyotes were introduced into the ecosystem, and so that really influences the duck population because the ducks are all of a sudden being eaten by the coyote, right? And so basically what's happening, density dependent and density independent are different ways in which a population are being influenced. All right, so is the population dying off because a giant hurricane hit? That would be a density independent factor. Is the population dying off because all of a sudden there's less plants because there's a drought? That would be there's less plants because like a different type of duck came in, is now eating them. That would be density dependent, right? Okay, so okay, so density dependent and density independent are just ways that a population are influenced. So if we look at this graph here, they have a couple of different things they also want you to know. There's a term called biotic potential, which is like the maximum productive rate under ideal conditions, meaning like in the ideal conditions, what is the maximum number of offspring that like a duck can have, right? So that's biotic, that's like the highest biotic potential. We already know that. And then the other thing is environmental resistance. So like this is what they're talking about here. So like what are the things that cause this carrying capacity to be capped? All right. So are they density dependent or density independent factors that cause this carrying capacity to be capped here? Okay. So essentially we're just building, a lot of this is very logical, and we're just building vocabulary to be able to describe these concepts and phenomena of various species populations. All right. Okay, so again, just to stitch things together, I want to revisit the carrying capacity graph that I showed before, the more complicated one. And so as we go through the multiple choice questions and the free response questions, think about what are the factors that make this carrying capacity where it is. And as there is growth, what are the resources that cause it to grow? What are the lack of resources that cause it to not grow, right? To stop growing as it hits the carrying capacity. So those are things to think about. Okay. So that's it for, this is a short video, but that was my quick explanation, or too quick of an explanation for the first half of Unit 3. So hopefully I can answer some questions that you guys have about it as you work through the multiple choice and the free response. Thanks for watching.